All right, so the main topic today is going to be multiplication, but I want to go back and go over a couple of addition and subtraction things that we have done and that you read about that I thought maybe we could use just a little bit more work on. So into the notes we get. So more fun. A couple of things related to the algorithms that we looked at for addition and subtraction are approximation methods and mental tricks that we can do math with. So for example, some mental tricks. There's a pattern that's pretty common called compatible numbers. And this is used for addition, subtraction, multiplication, and division. So we'll see it again. And compatible means, right, the things that fit together well. So suppose I had to add the numbers 17 and 12 and 13 and 25. So the compatible number approach, and this is kind of an approach that I often take in my head if I'm trying to add up this sum right here, is I grab numbers that fit nice together, right? So like 17 and 13 or 7 and 3 fit nice together because 7 and 3 make a 10. And I might actually, consider the ones with that and grab the whole number and say, oh yeah, that's 10, 20, that's 30 right there. Another version, and then I add the 12 and the 25 after that. So grabbing easy things to do first. Another easy version of that, 17, 12, 13, and 25, is somebody else might look at this list and see the 5, the 3, and the 2 all together make a 10, and then start combining that with other 10s. So they'd say, oh yeah, there's a 10, 20, 30, 40, 50, 67 is what they'll get for the total there. So compatible numbers just means to pick a pair of numbers that work well together. And sometimes it could be with a more complicated calculation where you look for things that are compatible. So for example, suppose I had 12 minus 15 plus 82 minus 61 plus 55. So when I look at this list of numbers and I have addition and subtraction I got to deal with, subtraction is a little harder for me and most people. So as far as the minus 15, I'm thinking of the plus 55 over there, and I would say those are compatible in my head. And so I could take the 5 away, which means 50, and then take the 10 away from 15, and that leaves 40. So that pair for subtraction was compatible to me. The 82 and the 60 is a pretty easy one to do right there because we can easily take a 1 from a 2 and a 6 from an 8. Okay, so we would get 21 there, and then we bring the 12 together. So it's some mental strategies besides compatible numbers are just kind of altering the order of operation. So I'm doing a reordering here. And compatible numbers is reordering, so you put numbers that work nicer together. Rather than just say 7 plus 2 is 9 and proceeding from there, we say, nah, 7 and 3 is easier, that's 10. Or 2 and 3 is a 5, but that 5 makes a 10. So it's just a manner of putting things together that fit well. And sometimes there just aren't compatible numbers in a list. Oh well, we just go about doing our business. Another mental strategy, and paper strategy for that matter, is equal additions, which we talked about before. I'm just going to take another twist on that, and I'll review the way I did it the other day too. Equal additions is a subtraction strategy. And suppose I had 11 minus 7. So this is a situation where we might have to borrow. If that 7 were bumped up to a 10, this would be a little bit easier. So what I do is I think, or write, if I just bumped both of these up by 3, then I would be looking at 14 minus 10, which is a way easier problem to do. The answer is 4. Okay, so the equal additions here is if I have to do a subtraction problem, I shift them both up by the same amount, and I get a result that works. Now, we did this a slightly different way the other day, so I'll just write down the way I kind of looked at it the other day. Suppose I write it over here as 11 minus 7 stacked, what I mentioned the other day is I would like that one to be an 11, because 11 minus 7 I can see as 4. Actually, that's not a good example. Let me use a different example, a harder one. Let's do 223 minus 47. So the equal additions that I used the other day was I can't do 3 minus 7, so I bumped that up to a 13 because I can do 13 minus 7. And maybe I would count up to figure that out if it didn't jump into my head right away, but I get a 6 there. Now I can't just make that a 13 without adjusting things, and the equal additions adjustment is since I added 10 there to the top number, I add 10 to the bottom number, but in the next place. So here's my equal addition. I added 10 to the top and 10 to the bottom. That allows me to come up with that 6 there. I can repeat that over here. 2 minus 5 I can't do. If that were a 12, I could do it. So there's no digit there, so I bumped that up from 0 to 1. So essentially, I kind of added a 10 or a 100 in each spot. So 12 minus 5 I can do. That gives me a 7. 2 minus 1 is easy. That's just a 1. So that's the version of equal additions I did the other day, where I add 10 in the top and bottom. In the green, I added 100 top and bottom. I'm making the same addition to each number. This is this only works for subtraction, and I'm going to show why it works on a number line here. So, number line, and 0, oops, pen back please. 0 is over here, and then let's say 10 is right over there, and then 20 would live about over here. And the numbers I'm looking at are 11, which would be about here-ish, and 7, which would be right about there. So here's 7, here's 11. Now I rewrote both of those numbers by taking the 7 and bumping it up 3 places. So I'm now looking at the 10. And the 11, I also bumped up 1, 2, 3 places so that it's now a 14. And so that's the new position there. And the point here is, highlighter, that the distance from 7 to 11 is the same as the distance from 10 to 14, because all I did is pick up each number and shift them the exact same amount. So both numbers just moved up the number line by 3 units. They're still the same distance apart. And that's what subtraction finds, essentially, the distance between 2 numbers. So that's why this equal addition works. So equal additions works because the numbers stay the same distance apart. So it's both an algorithm for computing subtraction, and it's kind of a mental trick to make a subtraction problem easier by choosing some convenient value to add to both that gives us a nicer pair of numbers. So 14 minus 10 is an easier subtraction than 11 minus 7. All right, next tactic. And we just got a new visitor. Let's see, show me who's here, Zoom. Or somebody must have just came and went, looks like. Welcome back. All right, so front-end approximations is something hopefully you read about, but I haven't talked about it yet. It is an alternative to regular rounding procedures. So suppose I had 343 and I want to add that to 264. A front-end approximation, this would be the front on this side, would be to just forget about everything but the hundreds digits and just say, well, let's approximate it by saying what's 300 plus 200. And so the answer would be 500. Okay? So I'm not rounding here. All I'm doing is taking the leading digits and adding them up. Okay? So that's a quick approximation. And normally the way it works is I don't rewrite it, I just think it. So I'll show it again for another example. Now I could improve that observation by including more than just one digit. So I can include the front 2 digits, like 340 and 260. And so then the 4 and the 6 gives me a 10, 3, 1, and 2 are going to give me a 6. So that's a better approximation. Okay, so front end quick approximation. And then this one is a better approximation because I used more information. So normally when I'm applying a strategy like this, suppose I had to take 3,572 and add it to 6,685. I would just look at this and say, well, 6 and 3 is 9, so 9,000 is a quick estimate, right? Approximate symbol there means I'm guessing at an answer. Right? So that's a quick front end approximation, but sometimes we might use more than one. So the 5 and the 6 is an 11, so that's really 1,100, which bumps that 9 up to a 10. So a better approximation is 10,100. So here's the second stage of a front end approximation. And I might just decide, hey, that's good enough. It's around 10,100. Okay? And again, that's an approximation of the actual sum, not the whole sum, because I'm just looking at the front information to give me the answer. Right? So it's an alternative to rounding. And sometimes when I do things like this is also called a truncation. So also known as truncation. And truncation just means to chop. So I'm not rounding when I do that 2-digit front end approximation. I'm just saying, just look at the first 2 digits and forget about the others, right? I'm just chopping off the 72. Look at 6,600 and just chop off the 10s and the 1s, okay? So that's why it's called a truncation. It's also known as a front end approximation. And that's a pretty common strategy that's used when teaching kids how to approximate stuff. It is not rounding, right? That's not the way I would round those 2 numbers. So front end approximations and truncation almost always lead to an underestimate. Rounding, on the other hand, will sometimes be an overestimate and sometimes be an underestimate. It depends on the other digits, right? So in this case, if I were to round instead, so if I do versus rounding, if I were to round to the second place, that would be 3,600. Round to the second place, and then the other one would be 6,700. And then when I put them together after rounding, I get what? 3, 1, I get 10,300. So this is an over approximation. This is an under approximation. So the actual answer is somewhere between 10,300 and 10,100. Maybe it's closer to 10,200. We won't know until we add the other information in there. So these are some topics up at the end of section 3.2 that I didn't completely talk about. I talked about rounding, I talked about equal additions, but we didn't yet get to talk about front-end approximations and compatible numbers. All right, so that is most of what I had from section 3.2. One thing I want to go over additionally before we do multiplication are to talk about some of the other algorithms I talked about, namely the left to right algorithm, the Hindu algorithms, and the complementary number one, and I'll show you one other cute one. At the bottom, if you already had your home page open for the course, at the bottom of Unit 2, you might need to refresh your page. There should be 2 new pages. A multiplication model example I added yesterday, and then whole number algorithms I just added today. Let's take a look at the whole number algorithms. And here I'm linking out to a PDF file that I put together, so you'll have to download it in order to open it. And I just typed up some notes on other algorithms. So I have a right to left, let's blow that up a little bit, right to left carry down, left to right carry down. We've got for addition, and then for subtraction, we've got Hindu. I haven't talked about absurd, but I will today. We the complement. I didn't talk about subtract up, and I'm not going to, but feel free to read about it here. McClendon's algorithm is a weird way to subtract. I'm not going to go over, but feel free to read about it. Low stress is wicked cool. I will talk about that one today. And then we're going to look at some of these multiplication algorithms. In this chapter, remember, we're doing two different things. We're modeling. We're getting physical about what these operations, addition, subtraction, multiplication, division mean. But then we're also showing processes, like how do we do it on paper? Forget about drawing a picture of it. That's a model. We have algorithms, which are just getting the job done. Okay, so let us go back to the notebook and just review a couple of algorithms. And I'm going to do subtraction here. And let's take the problem, how about 5,243 minus 1,628. So first thing I'd like you to do is just apply the standard borrowing algorithm, which is also called the renaming algorithm, to this and come up with an answer, and then we'll try it with some other methods. Okay, so let me catch up to you here. Oops, I have chats. What's going on in the chats? Okay, so we got an answer from Amanda. Let's see if I can come up with an answer too. 3,615. Hopefully we're all on the same page. So we would like to take 8 from 3, but we can't. So we borrow from the floor. So we put a 10 there. So we change that from 43 to 30 and 13. 13 minus 8 on a good day is a 5. Excellent. 3 minus 2, hey, that works. That's a 1. Don't need to do anything fancy. 2 minus 6, or 200 minus 600, we can't do. So we borrow over here from that 5, make it a 4,000. And so then that's now 12 or 1,200. 12 minus 6 is 6. And 4 minus 1 is 3, so 3,615. So this is, again, what we call the standard algorithm, or what I call the standard algorithm, because that's what most of us grew up learning. It's also known as the borrowing algorithm, or the renaming algorithm. So that describes this right here. So now we're going to try some other ones. So my favorite is really the equal additions algorithm. So let's try that together. So I have 5,243 take away 1,628. And it works similar to borrowing, but I don't really borrow. I can't do 8 minus 3, but I could if that were 13. Since I'm adding a 10 here, I add a 10 to this number too by making that 20 a 30. So bottom line is, if you bump up by putting a 1 to make that 3 to 13, then you add 1 to the next digit in the column, in the row below. So 1, 1. 13 minus 8 is 5. 4 minus 3, no problem, nothing special, that's just a 1. 2 minus 6 I can't do, so I bump that up 1 and I bump this up 1 to a 2. So 12 minus 6 is 6, and then 5 minus 2 is 3, and I get the exact same answer in a slightly different procedure. So that is called equal additions. Questions on that? Hopefully you tried that yourself using the equal additions method. Okay, so another method I used the other day was the complement method. So 5, 2, 4, 3, 1, 6, 2, 8. Subtract. So the way the complement method works is we make a compatible number to the bottom one, that's its complement. Complement refers, in this case, to the next higher place value. That's 1,000, so it'd be out of 10,000. So in my head, I want to figure out what's 10,000 minus 1,628. The trick to doing that is with the first digit, make a 10. 8 plus what equals 10? Well, it would be a 2. After that, you want to make 9s. What plus 2 here in the bottom is 9, so that would be a 7. What plus 6 gives me 9? Answer is 3. And what plus 1 gives me 9? The answer would be 8. So 8,372 is the complement of 1,628. And if you were to add the bottom number and the top number together, the green, bottom green one and the top red one, you would get 10,000. And the trick again is that these two digits here and here make a 10, and then the other pairs make a 9. 6 and 3 is 9, 1 and 8 is 9. Then the way the complement method works, once we make that complement, which is a pretty easy subtraction do, we just add the two top numbers together. So 2 plus 3 is 5, 7 plus 4 is 11, carry the 1, 1 plus 3 plus 2 is 6, and then 8 plus 5 is 13. And then we just cross out that extra 1 there, and there's the answer, 3,615. That's what's called the complement method. And that document I pointed out a minute ago has explanations of all of that, the rules and an example. So we can check that out later. Next one I did was the Hindu or the left to right algorithm. So 5,243 minus 1,628. So for this one, we start on the left side. So 5,000 minus 1,000 is 4,000. And then we would like to take 600 from 200, but we can't, so we borrow from below. 12 minus 6 is 6. 4 minus 2 is 2. 3 minus 8 we can't do, so we borrow from below. 13 minus 8 is 5, and there's my answer. 3,615 with the digits that aren't crossed out. And that is the Hindu left to right algorithm. So two more that I didn't go over last time that are in that document. One is called low stress, which I really like. And this is one that can help kids that struggle with the borrowing stuff here. And it relies on the idea that we're renaming the top number to be more compatible with the bottom number to do the subtraction. So the way it works is you write down, as usual, the top number, 5,243. And then you draw a rectangle, pretty good size, underneath. And you are going to have some work to go in there in a minute. And underneath that, you put the number you're subtracting. 1,628. So this is the setup for the low stress algorithm. And then what we do is we kind of think ahead of time about all the borrowing that has to happen. So I can't do 8 minus 3 here, so I'm going to have to borrow from that 4, which means it's going to become a 3, and that 3 there is going to become a 13. 3 minus 2 isn't a problem, so no big deal. And then here I have the 2 minus 6 is a problem, so I'm gonna have to borrow from that 5, make it a 4, and make this a 12. So I'm renaming the 5,243 as 4,000s, 1,200s, 3 10s, and 13 1s. So I'm renaming, I rewrite my digits here, because sometimes this crossing out and writing extra digits freaks some kids out, but this is a little cleaner. Now I just pay attention to each column. 13 minus 8 is 5, 3 minus 2 is 1, 12 minus 6 is 6, 4 minus 1 is 3. So it's just a slightly different way of writing our borrowing algorithm. It's called the low stress algorithm. You'll see it in some textbooks, and I think it is pretty helpful for a lot of kids that struggle with borrowing and subtraction. All right, next is an algorithm that kind of some kids spontaneously come up with on their own. So I'm not going to name it yet. I'm just going to write it down and try to explain what I'm doing as it goes. All right, you ready for this? So here I have to take 8 from 3. So what is 3 minus 8? Some kids will say, hey, that's -5. 3 minus 8, yeah, it's a -5. Some kids just get negatives from an early age. They also get place value. So then the kid might next go, okay, 40 minus 20, that's 20. Then they'll come over here and say, okay, 200 minus 600, that would be a -400. And 5,000 minus 1,000 is 4,000. And then they kind of put all that together. So let's see, 4,000 minus 400 would be 3,600, and 20 minus 5 would be 15, and there's the answer. So this is subtraction using negative numbers. There's one thing to call it. It's more often, instead of called the subtraction with negatives algorithm, it's more often called the absurd algorithm. Because there's a lot of people that think that's absurd. Why would you write a negative down there? Why not? And so that's a weird one that some kids just kind of naturally come up with on their own if they understand place values and the idea of a positive and a negative, a gain and a loss. Okay, so the first 3 up here were a review we covered before: the equal additions, the complement, and the Hindu in the last class. There's recordings about that. Low stress is just an alternate version of the borrowing algorithm where we just write it underneath instead of above with all this crossed out weirdness. And then there's the absurd algorithm, which just works with negatives and then reconciling the balance. Sometimes equal additions is easier to do for people if they know how to do it than the standard algorithm. Low stress can almost always be easier. Hindu for us is just weird because we're not used to going in that direction, but the more you practice it, the better you get. And remember, I'm not advocating you teach any of these algorithms in the future. I'm just trying to stretch your brain about the processes that we use to do stuff. It's not the only way to do it. And this algorithm that I'm calling standard here isn't standard across the world. It's just standard in the United States. Okay, so I think that's all I wanted to talk about in section 3.2. And I am ready